Okay, so in last lab we performed the two experiment, which is the experiment number 4 and experiment number 5. So experiment number 4 is actually about the half subtractor and the full subtractor, and the experiment number 5 is about the code conversion. So in that code conversion, we studied about the binary to gray and gray to binary code converters. So till now we already performed the 5 experiment. Now today we have to perform the experiment number 6, which is again one type of combinational circuit. So in that combinational circuit, the name of that combinational circuit is the comparator. So today we have to learn about the comparator. So now actually what is comparator? So from name also you can easily understand the comparator is the combinational circuit which is used to compare the two binary numbers. A comparator is a combinational circuit. Comparator is a combinational circuit which is used to compare two binary numbers. Okay, which is used to compare two binary numbers. So this is the application of the comparator. And sorry, this is the actually working of the comparator. Oh, okay. So first we'll learn about the comparator, the theory of the comparator, the truth table, and also a logic diagram. And then there are pre-test and pre-test. After pre-test, we have a simulation. And after simulation, we have a post-test, and then we end the session. Okay. So today we performed a single experiment, only one experiment, which is experiment number 6. Which is experiment number 6. So today we have to learn about the 1-bit and a 2-bit comparator. 1-bit and 2-bit comparator. So now, what is comparator? So again, the comparator is a logic circuit, or you can say it is a combinational circuit. It is a combinational circuit which is used to compare the magnitude of two binary numbers. It is used to compare the magnitude of two binary numbers. So if we compare the two binary numbers and if we want to check the magnitude of that two binary numbers, okay, then we have a three possibilities. Suppose I have a two binary numbers. I have a two binary numbers, you can say A and B. Okay, I have a two binary numbers, you can say A and B. So what is the possibility when we compare the magnitude of that two binary numbers? So the first possibility is either A is greater than B. The second possibility is either A equal to B. And the third possibility is either A is less than B. So we have a three outputs. We have a three outputs of a comparator, A greater than B, A equal to B, and A less than B. So comparator circuit provides the three output, A equal to B, A greater than B, and A less than B. So generally, which gate we are using for the comparator? A basic comparator. So exclusive NOR gate. Exclusive NOR gate is work as a basic comparator. Why? If anyone is remember the truth table of exclusive NOR, the truth table of exclusive NOR is 0 0. It is 1. 0 1 it gives 0, 1 0 it gives 0, and 1 1 it gives 1, and 1 1 it gives 1. So when the output of exclusive NOR gate is high, when both the input of a exclusive NOR gate is same, when both the input is same, then and then it will give the high output. Means when my both the input is same, means 0 0, or you can say it is 1 1, then and then it will give you the output 1, or you can say high output. When both the input are different, it will give you the low output. When both the input is different, then it will give you the output 0. So for 0 1 it is 0, and for 1 0 it is 0. So exclusive NOR gate is work as a basic comparator circuit, or you can say it is used for the equality. It is used for the equality. So you can see in bracket the output is 1. The output is 1 if and only if the output is 1 if and only if the input bits are coincide. Input bits are coincide. What is the meaning of coincide? The meaning of coincide is same. So the output is 1 if and only if the input bits are same. Input bits are same. So two binary numbers are equal. Two binary numbers are equal if and only if their corresponding bits coincide to each other. Their corresponding bits coincide to each other. Suppose we have a two binary numbers A and B. Suppose we have a two binary numbers A and B. Okay, and in that two binary numbers having both the binary numbers contain 4 bits. Both the binary numbers having 4 bits. So A having a 4 bits, A3, A2, A1 and A0, and B also having a 4 bits, B3, B2, B1 and B0. So when we can say A equal to B? When we can say A equal to B? If A3 is equal to B3, A2 is equal to B2, A1 is equal to B1, and A0 is equal to B0, then and then we can say A equal to B. So all their all the bits must be coincide to each other. All the bits must be coincide with each other. So what that means, if my A3 is equal to B3, A2 is equal to B2, A1 is equal to B1, and A0 is equal to B0, then and then I can say my A equal to B. A equal to B. So this is the equation of the equality. This is the equation of equality. So if anyone is remember, in a circle there is a dot. So this is the symbol of exclusive NOR gate. As we have a plus sign for OR gate, multiplication sign for AND gate, a dash or a bar sign for NOT gate. Same way, in a circle with a dot, it is a sign of exclusive NOR gate. It is the sign of exclusive NOR gate. So what is the condition for the equality? My A3 must be same with a B3, A2 is same with a B2, A1 is same with a B1, and A0 is equal to the B0, then and then we can say A equal to B. Then and then we can say A equal to B. So this is the equation of equality when we have a two numbers with a 4 bits. We have a two binary numbers with a 4 bit. But today we have to learn about the 1 bit comparator and 2 bit comparator. Our experiment is about the 1-bit comparator and a 2-bit comparator. Okay, we do not have to focus on the 4-bit comparator. So today we learn about the 1-bit comparator and 2-bit comparator. So anyone having any doubt in this comparator? If anyone having any doubt, you can ask me a question by unmute yourself, or you can ask me a question in chat session. And if it is no doubt, we will move forward. Okay. So I think no one having any doubt. So let's move for the 1-bit magnitude comparator. So again, we have a two binary numbers A and B, but both the binary numbers having only 1 bit. Both the binary numbers having only 1 bit. So the theory is 1-bit magnitude comparator. So suppose we have a two binary number A and B, and each having a single bit. So A0 is the bit of A and B0 is the bit of B. So we have a single bit A0 and B0. So now first we have to learn about the A greater than B. So if my A0 is 1, if my A0 is 1 and B0 is 0, if my A0 is 1 and B0 is 0, then we can easily say that my A is greater than B. Then my A is greater than B. But suppose, and what is the equation for that? As I already told you too many times, 1 means as it is, 1 means as it is, and 0 means bar, or you can say dash. 0 means bar, or you can say dash. So my equation is A0, A0, B0 dash. Then the second case, if my A0 is 0 and my B0 is 1. So if my A0 is 0 and B0 is 1, then my A is less than B. Then my A is less than B, and the equation for A less than B is A0 bar B0, or you can say A0 dash B0. So this is the equation of A less than B. The third one, if my A0 is 1 and B0 is also 1, so what that means, my A0 is coincide with B0, then it is A equal to B. And also there are another case also which is not mentioned here. Suppose my A0 is 0, my A0 is 0 and my B0 is also 0. My A0 is 0 and my B0 is also 0. Then also my A equal to B. Then also my A equal to B. So the equation of equality is the equation of equality is A0, the symbol of that exclusive node, or the symbol is, it is for the coincide. So A0 coincide with B0. A0 coincide with B0. And now we have to make a truth table. So A0 and B0. So we have only a single bit. So we have a 2-bit actually. So we have 4 different possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. And in table it is LEG So full form of LEG is L means less than, or you can say less, E means equal, and G means greater. Okay. So for 0, 0, you can see both are same. So we have for equal it is 1, and for less than and greater than it is 0. For 0, 1, so for less than it is 1, for equal and greater than it is 0, 0. For 1, 0, for less than and equal is 0, 0, my greater than is 1. And for 1, 1, again it is equal, so 0, 1, 0. So now we have this equation. We have the equation for greater than, we have the equation for the less than, and we have the equation for the equality. So now we have to draw the logic diagram. Now we have to draw the logic diagram. So this is first for equal. You can say here it is written E or A equal to B. So the equation for that is A0 exclusive nor B0. A0 exclusive nor B0. So here the first equation. The second equation is for the less than. So for less than we have the equation A0 dash B0. So here from here I am taking A0 giving to the NOT gate. So here we have A0 dash B0 and give it to the AND gate. And the third one A0 B0 dash for the greater than A0 B0 dash. So from again I am taking B0 here giving to the NOT gate. So here I have B0 dash and A0 directly given to the AND gate. So finally this is the 1-bit magnitude comparator. This is the 1-bit magnitude comparator. If anyone having any doubt in a 1-bit magnitude comparator, uh, you can ask me a question by unmute yourself, or you can ask me a question in chat session. Anyone having any doubt in 1-bit magnitude comparator? Okay, so it is clear. Also, we have to check the theory which is given in the virtual lab. So actually, this is our experiment number 6, but in virtual lab, it is the last experiment. You can say experiment number 12. Experiment number 12, verify the truth table. Verify the truth table of 1-bit and a 2-bit, 1-bit and a 2-bit comparator. 1-bit and 2-bit comparator. So come to the theory part. So you can see here a magnitude digital comparator is a combinational circuit that compares two digital or binary numbers. Okay, so comparator is used to compare the two binary numbers and which having a 3 output. Either it is equal or less than and greater than. So we have two input. We have two inputs and we have 3 output terminals. So we have 2 input terminal and 3 output terminal in a comparator. Okay. So this is the generalized block diagram of a n-bit comparator. So we have a two binary numbers which having n bits, but the binary numbers is two only. So we have two binary numbers A and B, and we have three output possibilities. Either it is A greater than B, A equal to B, and A less than B. So you can say a one bit magnitude comparator. So again, the one bit magnitude comparator is compared the two bits is called the single bit comparator. So it consists of two inputs and having a three outputs. So you can see the truth table which is we already seen. So we have two inputs. So we have four possibilities 0, 0, 0, 1, 1, 0 and 1, 1. And we have three output possibilities. You can see here A less than B, A equal to B, and A greater than B. And also we already checked the logic diagram. So these are the equations. From the truth table we are getting the equation, and from the equation we can draw the logic diagram. So this is about the one bit comparator. So let's move for the another circuit which is a two bit comparator. So again we have a two binary numbers, but now we have a binary numbers with a two bits. Binary numbers with a two bits. So suppose A1 and A0 is the bits of the binary number A, and B1 and B0 are the bits for the binary number B. Okay. So we have two bits in a binary number A1, A0, and B1, B0. So now first of all we have to make the equation for the A greater than B. A greater than B. So there are two possibilities for A greater than B. So the first one is if my A1 is 1, if my A1 is 1 and B1 is 0, if my A1 is 1 and B1 is 0, then it is A greater than B. Then we do not have to focus on A0 and B0. What is the value of A0 and B0? Okay, bits. You can say A1, A0, and here we have B1, B0. So here A1 and B1 are the MSB, most significant bit. Okay, so my if A1 is 1 and my B1 is 0, then my A must be greater than B. We do not have to focus on A0 and B0. Suppose in that case, if my A0 is 0 and my B0 is 1, then also you can see here we have 1, 0. So if you convert into decimal, it is 2, and here we have 0, 1. If you convert into a decimal, it is 1. So first, if my MSB is 1 and the MSB of another bit is 0, then we do not have to focus on the another bits. Then we do not have to focus on the another bit. So if my A1 is 1 and my B1 is 0, then my A is greater than B. Okay, so this is the first case. But in second, let's say if my A1 and B1 are same. Either both are 1 1 or you can say both are 0 0. Then we have to focus on the second bit, which is A0 and B0. Then we have to focus on the second bit, which is A0 and B0. Again, it is a second possibility. If my A1 and B1 is same, A1 and B1 is same, either my sound is breaking. I am not audible. Let me see my network. Wait for 1 minute. Hello. Now, is it okay? Hello. Am I audible? Okay, Mohit. Yes. Okay. So now in second case, suppose now if my A1 and B1 is same. Okay. So in first case, if A1 is 1 and B1 is 0, then we do not have to focus on the A0 and B0. But suppose if my A1 and B1 is same, either it will be a 1 1 or it will be a 0 0, then my A0 must be 1 and my B0 must be 0. My A0 must be 1 and my B0 must be 0. Then and then we can say A greater than B. Then and then we can say A greater than B. So you can see case number 2. So if my A1 and B1 is coincide, again I am saying what is the meaning of coincide? It is same. Coincide means same. So if my A1 and B1 coincide, then we have to focus on A0 and B0. So in that case, my A0 must be 1, my A0 must be 1 and my B0 is 0. My B0 is 0, then and then we can say A greater than B. Then and then we can say A greater than B. So now the equation of A greater than B, you can see here. So this A1 B1 bar, this A1 B1 bar are from the case 1. So here my A1 is 1, so A1 is as it is, and B1 is 0. So B1 is 0, that's why it is B1 dash. B1 is 0, that's why it is B1 dash. So A1 B1 dash. But here we have OR. OR means another possibilities. So OR means it is the OR gate. So you can say the sign of plus. So plus, if my A1 and B1 is coincide, so coincide means A1 and B1 is same. So which gate is used for the same? We are using the exclusive NOR gate. So A1 exclusive NOR B1. A1 exclusive NOR B1. In this case, my A0 must be 1 and B0 must be 0. So A0, B0 dash. So this is the equation of A greater than B. This is the equation of A greater than B. Now we have to focus on the A less than B. So the reverse of A greater than B. Now if my A1 is 0 and B1 is 1, if my A1 is 0 and B1 is 1, then we can easily say my A is less than B. But again, the second case, if my A1 and B1 is coincide, if my A1 and B1 is coincide, in that case, my A0 must be 0, my A0 must be 0 and B0 is 1. A0 must be 0 and B0 is 1, then and then I can say, my A is less than B. Then and then I can say my A is less than B. Uh, if you get the equation of A greater than B, just we have to change the sign of dash. Here we have a dash in a B, so we have to move the dash on A for the A less than B. Otherwise, the equation is same. You can compare both the equation. Here I have A1 B1 dash, so here I have A1 dash B1. A1 coincide with B1, it is remain same in both the cases. For A greater than B, I have the equation A0 B0 dash. For A less than B, I have equation A0 dash B0. So just switch over the sign of dash from B to A. So this is the equation of A less than B. And last, for the equality. So what is the condition for equality? If my A1 and B1 is coincide, and also if my A0 and B0 is coincide, then I can say my A is greater than B. Then I can say my A is greater than B. So A1 and B1 coincide, and A0 and B0 is coincide for the A greater than B. So this is the equation of A1 coincide with B1 and A0 is coincide with B0. So this is the equation for the equality, or you can say A equal to B. So now we have to draw the circuit logic diagram. So these are the three equations we have. The first for the A equal to B, second for the A less than B, and third is for the A greater than B. Okay. So from that equation we have to draw the logic diagram. We have to draw the logic diagram. Okay. So first for the equal, you can say A1 and B1 going giving to the exclusive NOR gate. So A1 and B1 is coincide. Then A0 and B0 given to the exclusive NOR gate. So A0 B0 coincide, and we have to multiply it. So for the multiplication, I require the AND gate. So output of A1 B1 exclusive NOR and A0 B0 exclusive NOR given to the input of the AND gate. Given to the input of the AND gate. So this is the equation for the equality. Then we require for the A less than B. Sorry, here we have first A greater than B. So what is the equation of A greater than B? You can see here A1 B1 dash. So here A1 and B1 dash giving to the AND gate. So we have A1 B1 dash. In second case, I required A1 exclusive NOR B1. So I am taking A1 exclusive NOR B1 giving to the one of the AND gate, and again we have three input AND gate. The another input are A0 B0 dash. So I am taking A0 B0 dash giving to the AND gate, and in between we require plus sign. So the output of both the AND gate giving to the OR gate. So we have finally equation for A greater than B. We have finally equation for the A greater than B. Same way, now we have to draw the circuit of the A less than B. So what is the equation of A less than B? A1 dash B1. So you can see here A1 dash and B1 giving to the one of the AND gate. So here I have A1 dash B1. Here I have A1 dash B1. A0 dash B0. So A0 dash B0 with A1 coincide with B1. A1 coincide with B1. So again, I am taking A1 coincide with B1. Again, output of both the AND gate given to the OR gate for the addition. So this is the logic diagram, or you can say a logic circuit of a 2-bit magnitude comparator. 2-bit magnitude comparator. So anyone having any doubt? Anyone having any doubt in 2-bit magnitude comparator? If anyone having any doubt, you can ask me a question in a chat session, or you can ask me a question by unmute yourself. Okay, so let's see the theory which is already also given in the virtual lab. So again, it is the same thing. We have a 2 bits. So 2-bit magnitude comparator. Again, we have a you can say 2 input and 3 outputs. So the 2 inputs are A and B, but A and B are having a 2-bit. So also you can say it is a 4 input also. So we have to make this truth table. So yeah, and we have 3 output. The output is A greater than B, A equal to B, and A less than B. So you can see here, suppose my input is, so we have 4 inputs. So how many possibilities we have? Actually 16 different possibilities, starting from 0, 0, 0, 0 up to 1, 1, 1, 1. I told you many times you have to remember this table of a 4-bit, starting from 0, 0, 0 to 1, 1, 1, 1. So you can see here the first is 0, 0, and here B1 and B0 is also 0. So A1 A0 and B1 B0 is same. So here it is A equal to B. Then 0, 0, 0, 1, second one. So now B1 B0 is higher than A1 is A0. So my A is less than B. So you can see here. Same way you can verify the whole truth table. Okay, same you can verify the whole truth table, and you have to write the truth table for the 3 outputs: A equal to B, A greater than B, and A less than B. Also from the truth table, we can derive the equation for the A greater than B, A less than B, and A equal to B. But so finally equation for the, you can see here, you can implement also this equation for the A less than B. This is the equation for the A greater than B. These whole are the equation for the A equal to B. But finally equation for A equal to B is A0 exclusive nor B0 and A1 exclusive nor B1. So from the equations, you have to draw the logic diagram. So this is the logic diagram for A greater than B, A equal to B, and A less than B. Now some of the applications of the comparators, and this is the main thing. If you have to ask the theory, you have to also write the comparator application. So what is the application of comparators? So comparators are used in the CPU. You can say the central processing units and the microcontrollers. Okay, so we have to use the uh, comparators in a CPU and also microcontrollers because having it gives suppose what is the application of the comparator in CPU? Uh, Suppose you have a closed loop control and you write one program. So and you have to compare the two numbers. So at that time you have to must require a comparator. So generally in microcontrollers and CPU we have the controllers. The another application of the comparator is the it also used to used in the physical variables such as temperature and position. Okay, so I have an example of that. Suppose you have a AC in your room. Okay, so when you start your AC and you set a temperature, suppose I am setting a temperature at 20 degree in my AC. So what that temperature indicates? That temperature indicates the reference value. That temperature indicates the reference value. But my room temperature is now 30 degree. My room temperature is 30 degree and the temperature set by me is 20 degree. So what comparator does? Comparator compares both the temperature. So there is a temperature difference. So comparator gives the signal to the AC to start the AC and start the cooling. Okay, so now cooling will be start. So again my room temperature start decreasing from 30 degree to 29, 28, 27, 26, 25, and each and every time my comparator compares the room temperature with a reference temperature, the reference temperature which we set. The reference temperature compares the temperatures with a reference temperature. So now my set temperature is 20 degrees. So you can say my reference temperature is 20 degree, and now also my room temperature is 20 degree. Also my room temperature is 20 degrees. So now both the temperature is same. My both the temperature is same. So what comparator does? Comparator does give the signal to the AC. Now stop the cooling. Now stop the cooling, and the cooling will be stopped. So most of if anyone use the AC, you can also experience this thing. So once both the temperature is same, your AC cooling is automatically cut off. Your AC cooling is automatically cut off, and it will work on the fan mode. It will work on the fan mode. Again, if your room temperature increases above 20 degree, so again comparator continuously compares the room temperature with your set temperature. Room temperature with your set temperature, which is a reference temperature. If your room temperature will be increased, again comparator give the signal to the AC that start the cooling. So these are the main application of the comparator. Also comparator is used in the process control unit and the servo motor mechanism. Okay, this is the main application in the field of electrical. And the last is the comparator is used for the password verification and biometric application. So again, in a security process, we have to use the biometrics. Okay, biometric application. So in biometric, we are using. So when you're biometric, you you put your biometric to that biometric security step, and at that time comparator compares your biometric with the recorded biometric. So the recorded biometric is work as a reference. The recorded biometric is work as a reference. So if both the biometric will be set same, if both the biometric will be same, then and then door will be open. Then and then door will be open. Otherwise, it will be not open. Otherwise, it will be not open. So again, then password verifications and the biometric applications, we have a comparator. We have a comparator. So you can see some of the students are setting the password in their mobile. So once if you set the password like 1111, so each and every time when you are logging, you are putting your password. Okay. So again in your mobile also there is a comparator. What it compares? It compares the given password and the set password by you. If it is same, then and then your mobile will be unlocked, and if it is not same, then your mobile will be not unlocked. So in pattern, in password, in face detection, in each and every where we are using the comparator. In each and everywhere we are using the comparator. So comparator is the main thing which we are using right regular days. You can see in your mobiles, in CPUs, in a security purpose, punch in and punch out. So these are the applications of the comparator. So anyone having any doubt in comparator? Anyone having any doubt in this? If you have a doubt, you can ask me a question by unmute yourself, or you can ask me a chat session. And if it is no doubt, please write down a clear in chat session. So we will move forward for the pre-test. Okay, so let's move for the pre-test. Okay, so the first question is all the comparison made by the comparator is done using one circuit, two circuit, three circuit, four circuit. Okay, yes, and Mohit gives the answer. What about others? I want a reply from the maximum students. Okay, I'm not asking from all to give the answer. Okay, Amit also gives the answer. So it is A. Okay. The second question is one that is not the outcome of a magnitude comparator. Okay, yes, and Mohit, Mon, Amit, Harsik already gives the answer. It is A minus B. Okay, very good. The third one, if the two numbers are not equal. Okay, yes, Mohit, Amit, I do not have to also read the question. Okay, Vrunda also gives the answer. Nisita also gives the answer. It's A. Okay. Which one is basic comparator? Okay, yes gives the answer. Mohit gives the answer. Okay, Vrunda also gives the answer. Okay, so answer given by uh, the student is D. And the last one is the comparator are used in a. Okay, yes, Mohit gives the answer. Amit Harsik gives the answer that it is C. Okay, so very good. So now I'm clicking on the submit quiz. So all of the answer given by all the answer given by all of you are right. So we have 5 out of 5. So now let's move for the simulation. Let me share the link with all of you. So you can also do the simulation by yourself. So let me show you the simulation of one bit comparator. All of you also do the simulation by yourself. Okay, so this is the circuit. So we have a power switch. So power switch, as I already said, all the ICs are work on the 5 volt supply. Without supply, it will not work. So we have to give the power supply to the all the ICs. Now we have the two inputs X and Y, and we have to compare it. So X and Y both are 0 0. So see, the X equal to Y LED is low. So what that means? Both are 0 0 means X equal to Y. So add to the table. Then 0 1. So my X is 0, Y is 1. So my X is less than 1. So here you can see the second LED will glow. Add to the table. Now 1 0. So 1 0. So my X is 1, Y is 0. So my X is greater than 1. So add to the table. And 1 1. So again both are same. So add to the table. So this is the truth table for the one bit comparator. We have simulator 2 also. So here we have to write the simulator 2 is for the verification of the truth table. So suppose here I am writing my A is 0, B is 0. So what that means, both are same. So my A less than B is 0, my A equal to B is 1, my A is less than B, greater than B is 0. Click on check. If it is correct, here the correct will be written. Then my A is 0, B is 1. So my A is less than B. So A less than B 1, all are 0. So again it is correct. Now my A is 1, B is 0. So my A is greater than B. Click on check. So now again it is correct and both are 1 1. Again my A is equal to B. Click on check, it is correct. So now I request all of you do the simulation by yourself of a 2-bit comparator. And if you have any doubt in a simulation, you can ask me by unmute yourself or you can ask me in a chat session. So I will give you a 5 to 7 minutes to do the simulation. Okay, so you click on the link which is shared by me. So when you click on that link, the simulator will be directly open and you have to do the simulation of a 2-bit comparator of both the simulator. Okay, so anyone facing any doubt in a simulation 2, a 2-bit comparator? All of you completed that 2-bit comparator in simulator 1 and simulator 2. In simulator 2 also? Yes. Okay. Again, it is the same thing, just you have to switch on the power. And now we have 2 bits. So x1, x0, y1, y0. So x1 and y1 are the MSB for the x bit, and x0 and y0, you can say it is least significant bit, LSB, okay, x and y. It's the same thing. So now x1, x0 is 0, 0, and y1, y0 is 0, 0. So both are same. So you can see here the LED will glow up x equal to y. Again, you can add it to the table. And how the connection will be uh, done, it is shown by here with a color code. So it is a difficult circuit, you can say, because we have to use the uh, actually a 5 AND gate, 2 OR gates, and 2 exclusive OR gate. And also we have to use here it is not shown. Here we are taking directly A0 dash, A1 dash, B0 dash, B1 dash, but it is not actually possible. We have to use NOT gate also. So actually we required AND or NOT and exclusive NOR gate. So there are lots of connection we have in a 2-bit. So you can see here. So the connection is somewhat difficult. So now, if all are the ones, so you have to check each and every step, because you have, when you are submit the lab manual for the experiment number 6, you have to complete this truth table starting from 1 to 16. Starting from 1 to 16 means 0, 0, 0, 0, 2, 1, 1, 1, 1. Okay. And then you can click on print. So by clicking on print, you save this in a PDF, and then you can copy paste it. Okay. So this is the circuit and the truth table. So now, yes, the simulator 2 is completed. So can you share your screen if it is possible? So I stop my sharing. So yes, can you share your screen? Okay, thank you. No, go for the simulator 2. Yes, simulator 1 is completed. Okay, very good. Hmm. So here we have you can see only two inputs A and B. So we do not have four possibilities like simulator one. So as yes also got the incorrect, because what we are getting mistake, first we are taking A0 B0 and then we can check, but instead of that we have to write 0000 0001 0010 0011 1000 like this. Okay, so now you can got the correct. So thank you, yes, for sharing your screen. So let me show you. So here instead of 1 we have to write 2. So 0000. What that means? A greater than B is 0, A equal to B, yes, A and B is same, A less than B is 0. So you click on check. So here there are the remarks, it is correct. Same way 00, then it is 01. So 01 means my A is less than B, it is not equal to or not greater than, click on check, again it is correct. Then after it is 0010. So again click on check, again see it is correct. Then the third one is 0011. Click on check, again see it is correct. The next one is 0100. Now my A is greater than B, not less than B. So again click on check, again it is correct. So that's how you can write the table. That's how you can write the table. So now let's. I think no one having any doubt. Anyone having any doubt? Otherwise, we will move forward for the post test. Okay. So let we move for the post test. Okay. So the first question of the post test. The purpose of digital comparator is to convert analog to digital, to create different outputs. Okay, so no need to write the, sorry, no need to read the options. So the answer given by Mohit, Yash and Vrunda, it is D. So the purpose of digital comparator is to compare a set of variable or unknown numbers. So it is used to compare the numbers. The second, a magnitude comparator is defined as a digital comparator which has blank. Okay, Mohit gives the answer. Yes gives the answer. So, okay, Amit also gives the answer. So the Mohit and Yes gives the answer. It is C. Amit gives the answer. It is D. But see, Amit, we have a comparator with a three output: A equal to B, A greater than B, and A less than B. So actually, correct answer it is C. It is not D. Comparator having the output terminals, three output terminals, A equal to B, A less than B, and A greater than B. Okay, so actually correct answer it is C. The next, in a comparator, if we get input, as A greater than B, then the output will be B1, A0. Okay, yes, and Runda gives the answer. So it is some of the misunderstanding, because in option also we have a B, My A option A answer B, my option B answer 1, my option C answer A, my option D answer 0. So can you write down either it is B or it is 1? Okay. So Mohit, yes, and Runda select the option B, which having answer 1. Okay, next one. How many inputs are required for a digital comparator? 1, 3, 2, 4. How many inputs we required? Okay, so yes, Amit, Vrunda gives the answer. It is C. So we have a two inputs in a comparator. Now the last question. An identify comparator. Okay. Yes, and Mohit already gives the answer. Again, let me read the question. An identify comparator is defined as a digital comparator which has only one output, two output, three output, or no output. So the answer given by the Yash and Mohit, it is A. So let me click on that. Let me submit the quiz. Okay, so all the answers given by you, all the answers given by all of you are right. So at last we have the references. So if anyone want to learn more about the comparator circuit, you go through these are the reference books. So you can go through these reference books. Also, there are some of the links, and there are also the YouTube video, which is so shows you actually how a comparator will work. If you are in a college, then we also perform the experiment like this. We are using the ICs. So the ICs we are using, it is exclusive node, AND gate, OR gate, NOT gate, and we are performing the experiment like this also, this only. Okay. So you can also perform the experiment. Uh, uh, which link? The experiment link? This link? YouTube link? In your WhatsApp group. Instead of WhatsApp group, let me share right now only. Okay. So if you are in college, we also perform the experiment in the breadboard. So most of the time we are using the experiment in a breadboard, and we can check the either the A is greater than B or A is less than B. So we also perform the experiment like this. Okay. So this is from my side. Now, anyone having any doubt in today's session? So in a 1-bit comparator or a 2-bit comparator, so you can ask me a question in a chat session, or you can ask me a question also by unmute yourself. And if it is clear, please write down a clear. So we end the today's session. Okay, so thank you everyone. So now uh, please write down your enrollment number for the attendance, and then we can end the session. Okay. So those who already written their enrollment number, if they want to leave, they can leave the session.
સર
Yes. Yes,
સર
Reyes.
એક્સપેરિમેન્ટ નંબર 4 ને ડેટ વહી ગઈ છે કાલે સબમિટ કરતો તો થતો નહોતો.
Okay. કઈ વાંધો નહીં, આ જયારે
તો હવે
એકવાર ઓપન કરી દેશું પાછું.
ઓકે થેન્ક યુ સર.